This is the last video on the time domain representation of linear time invariant systems. The various time domain representations are convolution integral in the continuous time case, or convolution sum in the discrete time case, linear constant coefficient differential equation or the difference equation in the discrete time case, block diagram representation, which is going to be the discussion of this particular video, state variable description, interconnection of systems is also going to be included in the discussion in this video. What is interconnection of LTI systems? A specific system may have two or more than two impulse responses. How are we to represent the overall impulse response? For this, interconnection of LTI systems is generally used. The impulse response of the component systems is considered, and they are represented as an interconnection of LTI systems. Let us assume that two impulse responses are present with impulse responses h1 of t and h2 of t. These two impulse responses may be connected mainly in two ways. One is they may be connected in parallel. The other one is they may be connected in cascade. Hence, the solution of the interconnection of LTI system is in finding whether the impulse responses are in parallel or in cascade and combining the net result to obtain the final solution. Let us go on to the interconnection of LTI system by considering the two connections in detail, namely the parallel connection and the cascade connection. Let us go on to the parallel connection of LTI systems. Here we have been given a system whose input is x of t and the output is y of t. Two constituents impulse response are present, namely h1 of t and h2 of t. The net result is represented here as x of t, h1 of t plus h2 of t, and the output again is retained as y of t. The summation is carried out here. How is this going to be represented mathematically? Considering it, we will be having this is x of t convoluted with h1 of t plus, this plus sign comes here, x of t convoluted with h2 of t, that is what is represented in the second case, and this could be equivalent to x of t is convolved with h1 of t plus h2 of t, giving us the same result. The same could be extended for the discrete time case as x of n into h1 of n plus x of n into h2 of n is going to be equal to x of n convolution h1 of n plus h2 of n. Next, let us go on to the cascade connection of LTI systems. Here we have the input is represented as x of t. There is an intermediate case represented as z of t, and finally y of t. This could be represented as, since it is h1 of t and h2 of t, it is just the convolution of these two, thereby giving us the result x of t is going to be given by convolving it with h1 of t, h2 of t, giving us the result y of t. Let us go on for this particular expression. First stage, we are convolving x of t and h1 of t, giving us x of t into h1 of t. Next, we are convolving the net result with h2 of t, that is represented here as convolution h2 of t. This could also be represented as, we could have it as x of t, convolve it with the summation, which is h1 of t convolve h2 of t. The same could be extended for the discrete time case, where we would be obtaining the result as same x of n, convolve it with h of n, h1 of n, convolve it with h2 of n, giving us as x of n convolve with h1 of n convolution h2 of n. Now let us go on to some problems to obtain a better idea how to apply interconnection of LTI systems. The first set of problems includes obtaining the block diagram representation given the expressions of the impulse responses. The first expression given is h of t is going to be equal to h1 of t plus h2 of t convolution h3 of t convolution h4 of t. This is going to be, first this is going to be represented as a parallel connection, hence we have, here we would have x of t and here we would have y of t, hence it is going to be h1 of t plus h2 of t, and this is again the result is in cascade, so it is h3 of t into h4 of t. Next problem is we need to obtain the block diagram representation for the expression given by h1 of t convolution h2 of t plus h3 of t convolution h4 of t. What would be the solution? These two would be connected in cascade. This is in parallel. Similarly, these two would be connected in cascade. Thus, that is what has been mentioned, drawn here. h1 of t, h2 of t, this is what is shown here, and this is again shown here. The summation is obtained here. Next, let us try to find out an expression for the block diagram. Given the block diagram, we are asked to obtain the expression for the same. How do we proceed with such a case? Here we would see it is h1 of t, h4 of t. Here we have a summation h2 of t plus h3 of t, and here again there is going to be a convolution with respect to h5 of t. So the result is going to be x of t is going to be convolved with h1 of t convolution h4 of t, and this is going to be a summation h2 of 3 plus h3 of t. That is what is represented here, and here it is not total summation, this is subtraction, so that has been considered here, and finally again a convolution with the last element, namely h5 of t. Let us consider one more problem to find out an expression for the block diagram shown. Here the block diagram shown is h1 of n, here it is h2 into h4 with a negative sign here, here it is h3 and h5 with a positive sign, and this is h6 of n. Since the expressions could be extended for the discrete time case also, the solution is going to be x of n convolution h1 of n convolution, here we have h3 of n convolution h5 of n minus the convolution of h2 and h4 of n, and final convolution is with respect to h6 of n. Next is the block diagram representation. The block diagram representation needs to be studied for the difference equation and differential equations represented for a LTI system. What is the need of such a block diagram representation? It gives us the interconnection of the elementary operations that work on the system, and it is more detailed than the previous two methods studied, namely the impulse response or the differential and difference equation, which give us only the input-output behavior, whereas here in the case of a block diagram representation, this is the major advantage of that is it helps us to give the internal computations and operations of the systems that are there in the representation is clearly described. However, one of the drawbacks of the block diagram representation is that it is not unique. For a particular input-output characteristic of a system, various block diagram representations could be used to represent the system output. This particular discussion is going to be for two specific block diagram representations, though more block diagram representations could be considered for implementation. For a block diagram representation, the base is a differential or a difference equation. Only the discrete time case is considered. So the differential equation given is 4r into y of t plus L into d by dt of y of t plus 1 by c integral minus infinity to t y of t d tau is going to be equal to x of t. Can we represent each of these parameters like addition, multiplication and integration using various blocks? this is exactly what the block diagram is expecting. Similarly, for a difference equation, we have almost similar terms: y of n plus y of n minus 1 plus 1 by 4 y of n minus 2 is equal to x of n plus 2 x of n minus 1. So, the terms required for representation would be adder or a addition element, a multiplication element, and a shifting element here. Now, let us go on to see what are the three elementary operations which are there in the interconnection of signals. The first one is the scalar multiplication. It is given by y of t is going to be equal to c into x of t, or y of n is equal to c into x of n, as can be considered in this particular case, where c could be 1 by 4, or here we could see c is going to be r. C is just a scalar value. Next is the addition component, which is going to be given by y of t is equal to x of t plus w of t in the continuous time case, and for the discrete time case it could be given by y of n is equal to x of n plus w of n. Considering a specific example for the discrete time case, we get it as y of n plus y of n minus 1 representing x of n and w of n respectively. Final case is the integration for a continuous time LTI systems, represented by y of t is equal to integral minus infinity to t x of tau d tau, which is represented here, and we want to represent an integration. How could it be represented as a block? And finally, the time shift for a discrete time LTI system, represented by y of n is equal to x of n minus 1. We have x of n. How could we obtain x of n minus 1? A shifting element is required, and this shifting element has been already introduced in problems as a block represented by S. This is the representation that we are going to employ. Let us go on in detail to each of these representations. The first one is the scalar multiplication. It is represented as just a line is there, and on that we write the value of the scalar represented by c. Hence, this represents y of t could be either c into x of t, or in the discrete time case it could be represented as y of n is equal to c into x of n, as given here. Y of t is equal to c into x of t, or y of n is equal to c into x of n. Next is the addition case. How are we to represent the addition case? A adder element has been introduced. This is just a summation block where we assume this is a plus sign and this is also a plus sign. Hence, the output y of t would be given by y of t is equal to x of t plus w of t in the continuous time case, and for the discrete time case it would be represented as y of n is going to be equal to, this is x of n plus w of n. This is going to be the case for the addition component. We have it as x of t plus w of t, or for y of n it would be x of n plus w of n. So the second element has been introduced. It is the adder. The first element is just a scalar element. And let us go on for the third element, which is going to be an integration or a time shift. The integration element is represented by a block like this, and the shifting element, as has been introduced for time shift problems, has been introduced as a S block. So y of n is going to be equal to x of n minus 1, and integration is going to be equal to y of t is equal to minus infinity to plus infinity x of tau d tau. For the block diagram representation, only the discrete time cases are going to be considered. Hence, integration will not be considered as it comes under the continuous time case. We have the two expressions given by y of t is equal to minus infinity to plus t x of tau d tau, and y of n is equal to x of n minus 1. Next, let us go on to the detailed representation of the block diagram using two simple representations. The first representation is, given a difference equation, y of n plus a1 y of n minus 1 plus a2 y of n minus 2 is going to be equal to b0 x of n plus b1 x of n minus 1 plus b2 x of n minus 2, how would the block diagram be considered? In order to consider this, a block diagram has been considered in this particular manner, and instead of going directly for the block diagram, let us try to first consider what has been done to simplify this particular difference equation. The first case is this input case has been represented as another variable, namely w of n. So w of n is going to be equal to b0 x of n plus b1 x of n minus 1 plus b2 x of n minus 2. This is the starting point of the block diagram representation that is seen in this case. The next one is, since we have got this as w of n, y of n would be equal to, as has been given here, w of n minus a1 y of n minus 1 minus a2 y of n minus 2. As this is w of n, y of n would be w of n minus these two terms. That is exactly what has been written here. And finally, we could see that when we rewrite these expressions, this is what has been obtained as the difference equation which was considered at start. So now let us try to start sketching the block diagram. In order to sketch the block diagram, first we have w of n. So we have the input x of n. The first element is just a scalar element, so we could write it as b0 into x of n. Scalar representation is shown with an arrow, and the value of the scalar is written above it as seen here. So this is b0 into x of n. Next we need two shifting elements, one to generate x of n minus 1, another to generate x of n minus 2. So we put a first shifting element here and generate the first input, namely x of n minus 1 from x of n. So this generates x of n minus 1. The next one, again we put another shifting element, hence we get it as x of n minus 2. Once x of n minus 1 and x of n minus 2 are generated, the next step is in multiplying with the respective constants b1 and b2 respectively. So we consider x of n minus 1 and we multiply it with b1. Similarly, we consider x of n minus 2 and we multiply it with b2. So now the terms generated are b0 x of n, b1 x of n minus 1 and b2 x of n minus 2. So this is b0 x of n, this is b1 x of n minus 1 and this is b2 x of n minus 2. Let us first generate the first adder between b1 and b2, that is what has been generated here. So this generates b1 x of n minus 1 plus b2 x of n minus 2, and the sum of that we add to the resultant is going to be added with the other value, namely b0 of x of n. So we have generated the first expression, namely w of n. Next, let us go on to consider how we would generate, given w of n, how we would generate the second expression or the overall expression. So for that, we have first considered y of n as the output, and as before we need to generate y of n minus 1 and y of n minus 2 by adding suitable shifting elements. Thus, what would be the case? Here we have y of n, the first shifting element has been added, we have generated y of n minus 1, the next shifting element is added and y of n minus 2 is generated. Next, with y of n minus 1, the scalar term a1 needs to be multiplied and the scalar term a2 needs to be multiplied. However, if we are to implement this expression, we need to consider it as minus a1 and minus a2. Thereby, with y of n minus 1, minus a1 is considered. Similarly, with y of n minus 2, minus a2 is considered. Subtractor is not a block representation, hence the subtraction has to be considered in the scalar term. So once we have generated the expression, now let us try to complete the second expression. So w of n is generated here. First, let us try to add these two elements as before. So we are going to add minus a1 y of n minus 1 and minus a2 y n minus 2. That is why the first adder is here. The next one is we would like to add the resultant to w of n to generate y of n. That is what is done in the last case. We have added the resultant of minus a1 y of n minus 1 and minus a2 y of n minus 2 to w of n, and we have got the resultant. Please note here the multiplication is just with an element 1, which means this is the same. So y of n is going to be equal to w of n minus a1 y of n minus 1 minus a2 y of n minus 2. Thus, this completes one form of the block diagram representation, popularly called as direct form 1 in signal processing applications. Next, let us go on to see what could be another method, as we have considered that block diagram representation need not be unique. One of the major drawbacks is large number of shifting elements are being used. How can we reduce the shifting elements? For this, method has been implemented, and thereby the second block diagram representation has been obtained. So, to consider the second block diagram representation, the same difference equation is considered. Y of n plus a1 y of n minus 1 plus a2 y of n minus 2 is going to be equal to b0 x of n plus b1 x of n minus 1 plus b2 x of n minus 2. The major concept in this is that the position of the input and output is interchanged compared to the previous block diagram representation. How has this been implemented? For that, what we have considered is, just like the previous dummy variable wn, now a dummy variable called f of n has been introduced. And as can be seen, this f of n is given as a combination with input, which is going to be represented here, and it is also a combination with the output, as can be seen in this particular case. Let us try to generate this and try to understand how this has been obtained. First, let us go on to the extreme right side and try to obtain y of n is going to be equal to b0 into f of n plus b1 into f of n minus 1 plus b2 into f of n minus 2. This could be obtained as, here we have f of n, so this is b0 into f of n. Next, we need to generate f of n minus 1. We have generated it by adding one shifting element. Another shifting element is available here. This generates f of n minus 2. So, f of n minus 1 and f of n minus 2 have been generated, that is required in the second equation's last two elements. Next, we need to multiply them respectively with b1 and b2. So, b1 into f of n minus 1 has been generated at this stage, and b2 into f of n minus 2 has been generated at this stage. Similarly, here b0 into f of n is also generated. So, the second equation has been first implemented, and as a result, what could we do next? These two terms need to be added as before with the adder. That has been done. The resultant needs to be added with the first element, that is b0 into f of n. That also has been done, giving us the second part of the equation at this stage, that is y of n is equal to b0 into f of n plus b1 into f of n minus 1 plus b2 into f of n minus 2. Next, let us try to generate the values with respect to x of n. Already we have generated f of n minus 1 and f of n minus 2. Generating these two terms, we would be getting minus a1 f of n minus 1 after the first shifting element, and after the second shifting element minus a2 into f of n minus 2. These two are added because there is no subtractor block. The negative sign has been considered here, and the addition takes place, giving us the resultant of these two terms here, that is minus a1 f of n minus 1 and minus a2 f of n minus 2. This is the resultant that has been generated here, and to this we need to add x of n, which is the input. Thus, the solution is going to be x of n plus these two terms, giving us f of n. Thus, the overall second block diagram representation has also been generated with fewer shifting elements, and this is popularly called as direct form 2 because the shifting elements are reduced, and this is a popular method of implementation for filters. In order to understand the block diagram representations 1 and 2 respectively, let us go on to two simple problems. The first problem gives us the difference equation is represented y of n plus 1 by 2 y of n minus 1 minus 1 by 8 y of n minus 2 is going to be equal to x of n plus 2 into x of n minus 1. Let us try to draw the first type of block diagram. If we recall, we remember that more number of shifting elements are required. So here we have y of n, and let us first generate this terms, that is, we need to generate y of n minus 1 and y of n minus 2. That is exactly what has been generated here. This is y of n minus 1, this is y of n minus 2, and here it is plus half, which means it will generate minus a1 as before. So this is minus half, and here already it is a minus half. Minus of minus will give us 1 by 8. So we have generated the first two terms, minus half into y of n minus 1, and the other term plus 1 by 8 into y of n minus 2, which is given here. Next, what we do is we need to also add y of n. So that is, here we used to have w of n, that is added to it, giving us the resultant y of n. Next, let us try to consider the other case where we have x of n plus 2 into x of n minus 1. One of the major differences from the previous problem is that x of n minus 2 is not present in this particular problem. In the example, we had x of n minus 2, which means this shifting element is not required. Similarly, this summer is not required because this summer adds these two elements. So we could see the implementation is done with one summer and one shifting element. So x of n is here, this is x of n minus 1. We are going to generate 2 of x n minus 1, and we are going to add these two, giving us x of n plus 2x of n minus 1 to be equal to w of n, and that we have equated it to y of n, w of n minus half y of n minus 1 plus half 1 by 8 y of n minus 2. Next, let us go on for the second representation, which was considered wherein we had only one shifting element. So considering the positions here, the shifting element is present here. We have here as x of n, here we have it as y of n. So we would be getting this as minus a1. We would recall that the theory generates this as f of n minus 1, f of n minus 2, and the respective equations. So here we would be having this as minus a1 and minus a2, which is minus half and plus 1 by 8 from here. And for the x term, we have only one term, that is 2. So this is 1 of x of n and 2 of x n minus 1. That is what has been generated here. These two terms are missing because we don't have to add this term to this. So this adder is removed. Similarly, this element is also not there because we do not have x of n minus 2. We will consider one. Let us consider the second problem. Y of n minus 1 by 9 y of n minus 2 is equal to x of n minus 1. This is a problem which is suitable for the first type of block diagram representation, hence only this has been shown. Let us go on to consider what is going to be the representation. Here we have y of n and y of n minus 2, which means we require two shifting elements as shown here, and here we require one shifting element because we have it as x of n minus 1, that has been shown here. Hence we have got this as x of n minus 1, and this would be minus 1 by 9 y of n minus 2. Thus the solution is going to be y of n minus 1 by 9 y of n minus 2 is equal to x of n minus 1. Attempting the second part of form 2 is left to the listeners. Next we go on to the references, which are as usual Oppenheim and Simon Haken. Thank you. This completes the concept videos for Unit 1.